This episode of Real Engineering is brought to you by Skillshare, home to over 20,000 classes that could teach you a new life skill. Last month, MIT revealed their ion-propelled plane, the product of 7 years of development and the first of its kind. A plane capable of sustained, powered flight with no moving parts in its propulsion system. Just as the Wright brothers announced to the world that powered flight was possible, this flight lays down a milestone for ion drive technology that could pave the way to future investment and development. It has the potential to drastically improve propulsion technology. Having no moving parts is a benefit that cannot be understated. Parts can be made lighter, as they no longer need to survive the stress of movement. Reduced stress means reduced maintenance and costs. But perhaps the most immediate benefit we can garner from this technology is reduced noise. With no noisy combustion or rotating aerodynamic surfaces stirring up the air, these planes are like gliding owls, a characteristic military contractors will be eager to take advantage of. But with current limitations, this may take some time to come to market. Let's investigate how this new technology works and where it needs to improve in order to compete with current technology. This technology has been in development for decades now, with many spacecraft already using variations on the idea to achieve highly efficient thrust systems. These engines work on a similar principle to the ion propulsion of the MIT plane, albeit in a very different environment that lends itself to the technology. Take the N-Star ion drive aboard the now retired Dawn spacecraft. This spacecraft used xenon as a propellant because it has a high atomic mass, allowing it to provide more kick per atom, while being inert and having a high storage density, lending itself to long-term storage on a spacecraft. The engine releases both xenon atoms and high-energy electrons into the ionization chamber, where they collide to produce a positive xenon atom and more electrons. These electrons are then collected by the positively charged chamber walls, while the positive xenon atoms migrate towards the chamber exit, which contains two grids, a positive grid called the screen grid and a negative grid called the accelerator grid. The high electrical potential between these grids causes the positive ions to accelerate and shoot out of the engine at speeds of up to 145,000 km per hour. At that speed, even the tiny xenon atoms can provide a decent bit of thrust, but even still, this engine provides a maximum of 92 millinewtons of force, about the same force a piece of paper will exert while resting on your hand. But in the vacuum of space, there is no air to sap away the precious energy we provide. With no drag or friction to remove energy, we gradually build our kinetic energy and gain speed. The Dawn spacecraft weighed about 1,220 kilograms at launch, with a dry mass of 750 kilograms after the propellant had been expended. So let's say it has an average weight between the two of 1,000 kilograms. Rearranging the force equals mass by acceleration equation, we can calculate the acceleration this engine could provide at 0.000092 meters per second squared. A tiny acceleration, but multiplied by a week, and our spacecraft is flying at 55.6 meters per second. Multiplied by a year, and it's flying at 2,898 meters per second. That's 8.5 Mach. The latest generation ion drives, dubbed the Next engine, can produce 3 times the force and have been tested continuously without stopping for 6 years straight here on Earth. That's enough force to accelerate that 1,000 kilograms to 44,651 meters per second, 130 times the speed of sound. This is an incredible technology that will revolutionize how we explore space in the near future, but here on Earth it has a completely different set of challenges. Here on Earth, planes pose a completely different challenge. Air will continuously sap away any energy we input into our vehicle through drag. And so, we need to create an ion drive that can provide more energy than air can remove while traveling fast enough to achieve flight. Not an easy task, and the fact MIT have managed it is mind-blowing. Let's see how they did it. They first needed to optimize their plane design for the application, reducing weight to minimize the energy required to maintain height, and minimizing drag to reduce any energy losses to the air. They did this using something called geometric programming optimization, which allows designers to specify constraints and design criteria to a program, which will then find the optimal design. After running multiple computer simulations, they settled on a plane with a 5-meter wingspan and a weight of 2.56 kilograms. It would require a flight speed of 4.8 meters per second with a thrust of 3.2 newtons. 3.2 newtons is vastly more than anything achieved by the N-Star or Next engines, but they don't work in entirely the same way. Ion drives for space need to carry atoms to be bombarded. Within Earth's atmosphere, there is no shortage of atoms to ionize and accelerate, and this helps counteract some of the negatives of the drag they also induce. The plane's propulsion comes from an array of ion drives carried below the wing. The positive anode was a thin steel wire, which helped minimize the drag it induced, while the cathodes were foam aerofoils covered in thin aluminium, these being light and capable of producing lift to offset their weight. In this case, nitrogen is ionized and attracted across the electric field, induced by the 20,000 volts of electric potential between them. The nitrogen ions collide with neutral air molecules along the way to provide additional thrust, creating something called ionic wind. Getting that 20,000 volts of alternating current is really the most difficult part, and the team had to design their own lightweight high-power voltage converter to step up the 200 volts of direct current drawn from the lithium polymer batteries. This energy storage conundrum, as explained in my electric planes video, is the biggest challenge facing any technology like this. So how does this compare to conventional propulsion methods regarding thrust-to-power ratios? A typical jet engine achieves a thrust-to-power ratio of 3 newtons per kilowatt, while helicopter rotors achieve a power-to-thrust ratio of about 50 newtons per kilowatt. This ion-propelled plane is estimated to have achieved a thrust-to-power ratio of 6.25 newtons per kilowatt. So if we could find a way of powering these devices that didn't require heavy batteries, could these ion propulsion engines be used? Scaling these propulsion methods is not easy, and individual electrode pairs have their limit in the current they can pass between them via ion transport, due to limits in voltage and choked flow within the electric field, just as air can become choked within a constricted pipe. This affects something called the thrust density, which is the area over which the thrust is applied. Jet engines have a very high thrust density at over 10,000 newtons per meter squared, so we can produce a great amount of force with relatively low area. Now, this plane achieved a thrust density of 3 newtons per meter squared, so it is generating very little force over a very large area. We can just about manage to provide enough force with 4 racks and 2 rows of these electrodes hanging far below the wing for a plane this light and slow. The issue here is the same issue that prevents batteries from being a viable solution for planes. Power requirements do not scale linearly with the mass of the plane, they increase with the square of the mass, while the power requirements to overcome drag increase with the cube of the velocity. So our ion propulsion power will need to scale with it, but we cannot simply hang racks and racks of these electrodes beneath our plane. They, along with the structures required to support them, would cause far too much drag, and in turn flight surfaces would need to scale to counteract the pitching moment this would cause, causing even more drag. This technology is still in its infancy, and there are engineers far more intelligent than I working to figure out ways to apply it. Just think that 114 years ago, the Wright Flyer managed to fly just 35 meters in its 11-second first flight. This ion-propelled plane managed 55 meters in 12 seconds, and who knows where we will be in 100 years' time. We, as a species, are continually growing and learning how to apply these principles. It's a fundamental part of the human experience to continuously develop your skill set. Just as I have been developing my segue skills by watching this course by Wendover Productions about how to make an educational video essay. You can learn about any number of topics on Skillshare, like app development or animation. New Year's is the perfect time to set some goals and learn a valuable life skill. These days you can teach yourself pretty much any skill online, and Skillshare is a fantastic place to do it. With professional and understandable classes that follow a clear learning curve, you can dive in and start learning how to do the work you love. A premium membership begins around $10 a month for unlimited access to all courses, but the first 1,000 people to sign up with this link will get their first 2 months for free. As usual, thanks for watching, and thank you to all my Patreon supporters. If you would like to see more from me, the links to my Twitter, Facebook, Discord server, subreddit, and Instagram pages are below.